I want to welcome those joining us online. If this is your first time joining us for our Sustainable Energy Seminar Series, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is an event that we do every other week during the fall and the spring semesters here at the Wisconsin Energy Institute, with the goal of highlighting cutting-edge energy research from across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop solutions. So throughout the series, you'll hear from folks in engineering and science, as well as social sciences and humanities, to learn about the ways in which they view sustainable energy challenges and solutions. The seminar is open to the public. It's also a course for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. And it's presented in a hybrid format. You're welcome to join us here at the Wisconsin Energy Institute in person. If you do need to join us online, we do have that option available as well. For those who are joining online, live captioning is available. I will turn that feature on. You can click the Show Captions button in the bottom of Zoom to turn that feature on for yourself. And if you do have a question for our presenter today, you can use the Q&A, and I will interrupt if necessary to relay that question to our guest presenter. So with that, I'll introduce our speaker today is Dane Morgan. He's a professor in material science and engineering here at UW-Madison. And his research group combines the thermodynamic and kinetic theory and computational modeling of atomic scale processes to understand and design materials. So application areas include nuclear materials, batteries and fuel cells, earth mantle materials, sorption at water mineral interfaces, and electronic materials. And he's going to go into a little bit more detail about one specific application looking at fast oxygen kinetics and how that relates to technologies like fuel cells. Welcome.
All right, thank you very much. So I want to thank Scott for the invitation to be here. And thank you who came in person to participate, and welcome everybody online. As Scott said, please chime in with questions as we go. We can adjust the pacing as needed to have any discussion that's useful. So yeah, my name is Dane Morgan. I'm a faculty in material science and engineering, so I do materials research, but often materials related to different kinds of energy technologies. And one area which I've been working on for a number of years is materials that can move oxygen quickly. And I tend to primarily do my work computationally, meaning I do work where I design these materials and try to discover new materials using the computer. And then we do limited targeted experiments to help actually bring the materials into the real world. I do want to start by acknowledging a number of staff and postdocs at University of Wisconsin who have really been the people who did the work I am showing, and also collaborators at the National Energy Technology Laboratory who have helped us with a lot of these studies. And I want to acknowledge our research group who keep everything running and make it fun every day. And I'll finish by acknowledging funding sources, both in the form of actual resources to pay people and computing resources to do the computations that we do from a number of different places over the years. So here's a brief outline of the steps. I want to talk a little bit about fast oxygen materials and why they're interesting and important. And then a couple of efforts we've made to discover new materials using computational techniques, and then finish with one of the sort of more exciting areas where we're having a real transition to new technologies, which is around using machine learning and data science. Okay, so what are fast oxygen materials and solid oxide cells, which is what we're focusing on for their use? So a fast oxygen material, not too surprisingly, is something that can move oxygen quickly. And that can mean moving oxygen in the material around. It can also mean exchanging oxygen through an interface like the surface with oxygen gas. Oxygen is the essential part of fuels in many, many situations, right? If you're not doing nuclear technology, you're very often reacting with oxygen in one way or another. So it's pretty important in a lot of different technologies to be able to move oxygen around effectively. So solid oxide fuel cells, solid oxide electrolytic cells, oxygen sensors, also gas separation membranes, chemical looping systems that essentially pull oxygen in and out of molecules. All these are different contexts where fast oxygen conductors are used or could potentially be used to be effective, even in electronics technologies, some new memristor technologies also use fast oxygen transport. Increasingly prevalent in many different types of technologies are materials that can move oxygen around quickly within the material or across its interfaces. Now, I'm going to be focused primarily on developing materials where we have in mind the application of solid oxide fuel cells. They don't have to be used for that, but it's nice to have a specific application in mind so you can talk within that context. So here's the basic idea of how a solid oxide fuel cell works. You bring in oxygen gas on one side, you bring in fuel on the other. That could be hydrogen, could be methane, something with hydrogen and carbons typically. And if you react oxygen with hydrogens and carbons, you get stuff like H2O and CO2. Those are more stable. That means you can get energy out. In traditional combustion, that just gives off heat, and you use the heat to drive pistons, expand gases. In electrochemical applications, which is what we're focusing on here, you need to separate the two steps of that reaction of moving ions and moving electrons. That's kind of the magic of electrochemistry. So what solid oxide fuel cell does is it brings in oxygen atoms, changes them to a solid phase oxygen 2- atom, and and then moves it through an electrolyte over to the fuel. But the electrolyte doesn't let electrons pass. It only lets the ions pass. So when the oxygen gets to the fuel, it reacts with the fuel, and it needs electrons, and the electrons get pulled through an external circuit. Actually, goes the other way in terms of the motion of the electrons. They actually get pulled in when you form the oxygen. But the point is you're moving electrons around in order to complete the chemical reaction. And those electrons, because they're not allowed to pass through the electrolyte, are forced through an external circuit, and that gives you voltage and current and power. So that's the basic idea, and we're going to focus a lot on this part of the system, which is where you have to move oxygens across an interface and into the material. But moving oxygen through the electrolyte is also another critical area where fast oxygen transport is really important. Why do we care about these types of solid oxide fuel cells? They have a lot of really nice properties. They are a very efficient way to burn a fuel. If you're going to react hydrogen and oxygen, this is one of the most efficient ways to react them and form water and get out energy, generally more efficient than just reacting them and burning them and creating heat. It can burn a lot of different kinds of fuels. You can do a lot of different size systems very easily. And there's a lot of opportunity to maybe replace traditional combustion applications with something that is more efficient use of our fuels. So one of the areas which has been of particular interest is distributed power sources, where you might take biogas or methane and react it with, or natural gas, and react it with oxygen in your solid oxide fuel cell and very efficiently generate power, maybe on site for buildings, distribute your power generation. Oh, I have to keep moving, or otherwise. All right, I'll let Scott move around there and try. So here's an example of a picture of from Bloom Energy, which is a company that makes fuel cells for generating power for buildings. These are some of their Bloom Energy servers outside of the eBay headquarters. You can use them for efficient energy generation in aerial and undersea vehicle applications, for auxiliary power, backup, say for trucks or things like that. I don't know, but I bet California somewhere. But I don't actually know where it's located. More recently, there's been increasing interest in essentially reversing how a solid oxide fuel cell works. And so instead of, say, reacting hydrogen and oxygen to get water, you split water to get hydrogen and oxygen. A lot of very similar processes that involve moving oxygen quickly and a lot of the same materials. And so that makes a solid oxide electrolytic cell. And those can be paired with solid oxide fuel cells, sometimes even in the same device, as an efficient way to split water and generate fuel in the form of hydrogen, and then react the hydrogen back and get energy out where you want to. So there's a lot of interest in sort of generating hydrogen and then using hydrogen efficiently in fuel cells and in electrolytic cells. So all these are kind of coupled technologies. A lot of interest in using hydrogen burning fuel cells for things like heavy vehicles, marine and aviation, areas where batteries are just not quite the kind of energy density that you might like. Here's an example of, again, Bloom Energy partnering with Samsung to to make solid oxide fuel cell powered giant ships. Here's the efficiency, or essentially the voltage at which you can split water to get hydrogen from a number of different processes, and the solid oxide electrolytic cells. This lower voltage tells you that it's a more efficient process when you do it with these solid oxide cells. So a lot of the interest in the new interest in hydrogen economy aspects can couple very well to both the electrolytic cells and the fuel cells with these materials. So again, more reasons to be interested in developing materials that can exchange oxygen and move oxygen quickly for these applications. So what is an issue with a lot of these applications is that the efficiency of doing things, if we focus on the fuel cell application, say of splitting oxygen and getting oxygen to move around, is not great when you go to low temperatures. So this is just a plot of essentially the energy you lose when you split an oxygen and use it in a fuel cell. It's area-specific resistance. So if you think of just a circuit, it's essentially the resistance that this is going to create in the circuit when you have a cathode of a fuel cell that is moving oxygen around. And if you plot that area-specific resistance, this is the cathode line right here. What you'll see is as you plot it versus temperature is it's nice and low. This is a good low resistance. And then it begins to shoot upward and down near 650, 700 degrees Celsius. So value down here near 0.1 is quite workable. You don't lose much energy that way. But if you go up 10 times that, you really have a problem. You really can't operate your device in any practical way. It's just too inefficient. And this isn't a huge temperature range. Maybe from, you can get down to maybe 900, 800 with slightly better materials in this plot. But you go down to 600, 650, and you end up with a lot of struggles. Now, operating at 800 degrees Celsius can have some advantages, but it has obvious challenges. It is super, super hot. You're going to have a lot of materials degradation. If you were like, oh, cool, I'll use this in my cell phone, an 800 degrees Celsius device in your cell phone might not be the best idea. So it creates limitations. So there's a lot of interest in trying to flatten out this curve so that you don't get so much resistance down at lower temperatures. And that means more efficient materials, materials that can split oxygen efficiently, move it through the interface efficiently, move it through the bulk of the material efficiently. So this is a big motivation for us, is losses in the cathode of solid oxide fuel cells. But this kind of problem persists in a lot of these oxygen transport technologies. So if we just focus on what's going on, I can sort of illustrate why this process is challenging. What we're trying to do is bring in oxygen gas and end with oxygen ions in a solid form so that we can move them around to the electrolyte and go bring them over to the fuel. This involves some pretty complicated atomic scale processes. O2 molecules come down, they land on the surface. In the most efficient materials, they tend to find vacancies in an oxide cathode material. The vacancies grab one of the oxygen and pull it, allow it to transport through the material, and then other vacancies come out and replace it. And the sort of kinetics of this whole process, grabbing the oxygen, moving the vacancies around, that's what creates all the resistance that gives you losses at lower temperatures. So we want materials that can move vacancies really quickly, can grab oxygen from O2 molecules really efficiently and quickly. That's sort of our design problem. And the question that I came to this field with maybe 10 or 15 years ago was, can you use computational simulation methods to help design these materials? Is that something we can get to? And if the answer was no, I probably wouldn't be talking about it. So the answer is actually yes, you can. And increasingly, we're getting actually, I think, pretty good at it as a community. So it's an exciting time to share some of the things we're able to do now. So I don't really have time to go through all the great work that's being done in this community, so I won't even try to do that, but I don't want to give the impression that I'm the only person doing work like this. There is a lot of really exciting work. And so just to give a sense of the kinds of things that people are doing, I think there's two big classes. One is just understanding what's going on. What materials segregate to surfaces, what elements, how does that affect things? How do atoms diffuse around? What are the mechanisms? How does oxygen exchange through the surface? How does that relate to the defects on the surface? These are all really seminal papers that helped us understand those things. And that was a big focus 10 or 15 years ago, because we were just trying to understand what was going on, and modeling was good enough to be able to do that. What has happened in the last 5 or so years is we've gotten so good at the modeling and our understanding has improved that we're really being able to discover new materials. So this is a new interstitial diffusing material that was really discovered computationally. He's multiple materials that can move oxygen reasonably well that were discovered with computational methods, these in the last 5 or so years. So a lot of people are doing work like this. I'm going to share my work, but I don't want to give the impression that it's the only thing out there. So now let me step in and just give a few examples of the kinds of things that we've been doing. And what I want to actually start with is maybe the most important take-home message of this, even if you're not particularly interested in oxygen conductors or these particular fuel cell technologies, which is what I'm going to show you is a couple of examples of what I would call modern materials discovery, which is really a bunch of tools that have come together over the last 20 or so years, I would say, to now all work in a really synergistic and effective fashion to allow a kind of materials discovery which wasn't possible even 10 years ago, maybe even 5 years ago. It was starting to really occur. And now it's become commonplace, and it's really very powerful. So I want to give you a feeling for how it works. So the way this approach happens is you can think of it like a big inverted funnel. You start with a lot of things, and you're going to sort of trim it down to end up with a small list of target materials. So what you want to do is start with a big list of candidate materials. And one of the things that's happened over the last 10 years is we have gotten large, accessible public databases of tens of thousands, hundreds of thousands, in some cases millions of candidate crystal structures of materials. These are all inorganic materials typically, although there's also organic databases. But for these applications, these oxides are inorganic materials. And these databases are an enormously valuable resource, and you can write fairly simple programs and just pull out tens of thousands of candidate materials that might be good fast oxygen conductors in this case. But you could also do it for materials that might be good solar cells, that might be good thermoelectric materials, whatever your application is of interest. You can start with a database of tens or hundreds of thousands of systems. Then we use simple, fast methods to start to remove systems that aren't promising. This can be as simple as these elements cost too much. I'm going to remove anything with certain elements like scandium or platinum. You're probably not going to make a fuel cell out of plutonium, so you can just get rid of any compound with plutonium. So you simplify. Some of those rules are simple. Sometimes they're subtler. They codify knowledge of the field about how to think about a material. Sometimes they're pretty sophisticated machine learning models that still run very quickly and help predict properties that you know are going to be promising or that are going to be problematic for your application. Once you've done that, because that can be done often in just a matter of minutes or hours because these screenings are very, very quick, then you go and you do more detailed molecular modeling. And this is where you really simulate how the atoms behave, how oxygen transports in my situation, or what band gap you have if you're designing solar cells. These tend to take hours or days even to do a single calculation. If you have a bunch of computers, you might be doing 10 or 20 a day, but you don't want to screen thousands and tens of thousands of materials this way. You want to screen dozens or 100 maybe. Then when your most promising materials come out of this more careful, detailed screening, now you hopefully have a handful, 5, 10 candidate materials. Now you go into the laboratory, which is typically the most expensive, most time-consuming part, but you're just working on a very small set of target materials. So that's the spirit of this kind of computational design. And the advent of online databases, new data-centric machine learning type methods, and very fast, very stable, scalable quantum computing methods, all of that has come together to make this really an incredibly efficient process for discovering new materials. So I'll talk about how we did it for discovering a new cathode material for a solid oxide fuel cell. So 3 of the most critical properties you might want for a cathode material. Let me remind you what our material is supposed to do. We would like to be able to design a material that will do this kind of thing. It will sit in a fuel cell. It will take in oxygen, exchange it with the surface, move it through the bulk. It will hang out there at 700, 600 degrees Celsius for typically thousands of hours. Like this is years and years of operation. You want it to be stable. And you want it, of course, to be reasonably cost effective and things like that. So the main 3 properties that involve pretty subtle physics that you want to get right is you want to be able to exchange oxygen really fast with the environment. If you can do that, you can get oxygen into your material. Typically, if you exchange oxygen fast, you'll move oxygen fast. So you want it to be active with respect to oxygen. We're going to quantify that with a quantity called K star, which is called the surface exchange coefficient. It just measures how fast you can exchange oxygen with the surface. You want it to be thermodynamically stable. If it's not thermodynamically stable and you put it at 700 degrees Celsius for 5 years, something's going to happen to it. It's going to come apart on you. And you want it to be electrically conductive because it is an electrode of a fuel cell. It has to move electrons around or you're going to have problems. So those are 3 pretty essential properties. So we're going to start by screening for those. There are other things you might want. You might want it to be have a low thermal expansion coefficient so it doesn't delaminate from another component of your fuel cell, things like that. But we didn't start by screening for those. We went for these 3 core properties. So how are we going to screen for these properties? So remember, I talked about these sort of simple heuristic rules. It turns out calculating with molecular methods the surface exchange coefficient is really hard. We've actually done it once. It took us about 7 years for one material, one surface of one material. So if we want to screen hundreds or thousands of materials, it's completely impractical. So we needed a simpler method, and we came up with a semi-empirical method for doing this. And the idea is, it turns out that if you just take 20 or 30 or so experiments of the surface exchange coefficient, and you relate it to the properties of the electronic structure of the oxide, it's something called the p-band center, and I won't go into the details of it, but it's basically a property of what the electrons on oxygen are doing in the material. And it's pretty easy to calculate. And it turns out that they're related, and this isn't crazy. It's not crazy that the way oxygen moves through the material depends on the properties of oxygen in the material. And it turns out, if you plot the log of the surface exchange coefficient, it's approximately linearly related to this simple p-band center. So now I have something I can calculate in a couple hours, and I can get a approximate estimate of the surface exchange coefficient.
I do have a question online
Yeah.
from John. So he says, do you analyze the heat loss rates from these high temperature systems and how it affects the practicality of the compounds discovered?
So I don't do that. That is a good thing to do. Typically, I think the compound that you are using for, say, the cathode doesn't have a huge impact on the overall heat loss rate through a fuel cell stack because that can be controlled by external insulation and things like that. So it's not, I think, a critical part of this materials choice, except in the broad qualitative way that if you get a good fast material and you can operate at lower temperature, it's going to be easier to maintain that temperature, right? However you maintain the temperature, the closer it is to room temperature, the easier it's going to be to manage.
Could you explain what is a perovskite? Is that derived from a name, I assume?
Yes. So sorry, I should have said that. So we're going to choose a class of materials to look at that are called perovskites. I do not know where the name came from, to tell you the truth. It is a widely used class of materials. There are thousands and thousands of different types of perovskites. They are used in a number of different types of applications. They're used as actuators because they can change their dimensions in response to electric fields. So they're ferromagnetic, they're ferroelectric. Anyway, there's lots of different applications. But most of the most promising materials are perovskites for this type of fuel cell application. So we limited ourselves to that space of materials to start with. Was that another question?
Someone just posted the link to the Wikipedia for perovskites.
Oh, okay. Thank you.
I don't see like, I guess it was named after a mineralogist from Russia, Lev Perovsky.
All right. I think strontium titanate may be the parent compound. That might be the first perovskite. But I see another question, although I didn't see the whole
And then, yeah, Bob asked to make sure it's adequately thermally stable. What container properties are necessary to not react or melt in the field?
To make sure it's so you're asking sort of what outer containment properties?
So
Yeah, I may not be the right guy to ask because I don't build fuel cell stacks. I don't know what the insulating materials are. A lot of the components are things like stainless steels and stuff like that that can handle these types of temperatures. But I don't know the exact materials that are used right now for the sort of casing outside parts of the fuel cell.
He just says containers may be later issues.
Yeah. Again, I think the type of containment engineering you do isn't very strongly coupled to the specific material you use. You do have to take some care that there aren't materials interactions with those, but typically you could swap in a different system without different materials that at the cathode level without having to change the rest of the fuel cell stack setup. Okay, so this gave us access through a reasonably easy calculation. This is a quantum mechanical calculation that we would do to the surface exchange coefficient. So now we could calculate this hundreds or even thousands of times and get an approximate value for how active our material was. We can also figure out if our material is thermally stable. And here we use these online databases I talked about, particularly the Materials Project, which has essentially all of the known solid phase compounds, has their energies calculated. So we can take a new compound, a perovskite, and we can actually use tools in the Materials Project to tell whether it's going to be stable with respect to decomposing to other phases. So it's a very powerful way to get at least an approximate guide about whether your material's likely to be stable. And we can calculate the band gap of the material. So band gaps, essentially, if they are zero, you have a metal. If they are not zero, you have some kind of semiconductor or insulator. So if your band gap is very low or approximately zero, then you are likely to have a reasonably good electronic conductor. It's not a perfect test, but it gives you some qualitative guidance that you're likely to have a good electronic conductor. And when we do our quantum mechanical calculations, we get these things called densities of states, which will give us information about the band gap of the material. So we can... Is there what?
LA, is that lanthanum?
LA is lanthanum, yeah. We'll see.
Economically viable?
Yeah, it is actually. I mean, it's a rare earth compound. So if you are building these out at a huge scale, you might have sourcing problems, and you might have to get it from some region like China or something where it might become difficult. But at least on the scale that right now people are manufacturing solid oxide fuel cells, it's not a critical issue. It's a smaller scale than, say, electric vehicle batteries, where you need maybe much larger amounts of material. So once we have the ability to calculate those those essential properties in a reasonably quick fashion, we can do this kind of inverted pyramid type activity. We start off with a big database of perovskites. Here we took some of them from known materials and we added in lots of permutations of different elements that we thought could be promising. Came up with about 2,000 different compounds. And then we started eliminating ones that didn't have a fast surface exchange coefficient compared to present day materials. We eliminated ones that weren't thermodynamically stable, or at least pretty close to thermodynamically stable. And we eliminated ones that our calculations suggested would be insulating. And we ended up with a moderate set of promising materials. If you put those back on this plot of surface exchange coefficients, these green dots were all materials that we predicted. And what we want is sort of stuff out here that has very high surface exchange coefficients and therefore is likely to be very kinetically active. So a little aside on what do we do with a list of materials like that. So the way to think about, I think, this sort of computational screening, these suggested materials, is a little bit like a strange extra robotic lab partner, right? Regular human lab partners have very strong common sense and basic understanding of your problem. They're going to make sort of logical suggestions. And they have access to some facts, but their knowledge isn't very comprehensive because it's just too hard to remember everything. Your robot lab partner has many, many facts, right? We gave them thousands of materials. We gave them lots of correlations, a huge amount of understanding and correlative knowledge. It's just very hard for humans to do. But they don't have any common sense or understanding. So they will suggest materials that make no sense unless you're a little bit careful. So you have to take what they say with a grain of salt, but you also want to listen to them because they know a lot about data and correlations that might be very hard for you as a human to get your head around. So when we look at all these materials, we didn't just grab the top one. And if you go and dig into the top one, you look at it and you go, I feel like there are other things I know about material science that tells me that this might be a little hard to synthesize, or might be a little too expensive to make, or something like that. So we actually picked a material which was similar to some other compounds that people had made. So a lot of these elements had already proven promising. Iron and cobalt and barium had all been used before. But what was really interesting about this compound is it had a lot of zirconium. People had played with zirconium, but not that much, because they expected a lot of zirconium, it's not a transition metal, to sort of shut down the material. But these calculations predicted actually the material would still be pretty good. So we said, all right, this is kind of a safe compromise. It's new, but it's not so new that we have no idea what we're doing. We expect it to at least have some activity. We can change the zirconium content a little bit if we need to. So let's see what happens if we use it. Now, the first worry we had was we know zirconium tends to make an insulator if you have too much of it. So we calculated, and we also, there's the band gap worry. So we checked the band gap, but it seemed like it wasn't too bad. There was also the issue of stability. A lot of these compounds that were similar to this had been studied, but they weren't very stable. And we knew that was going to be a problem. So we looked at stability as a function of zirconium content in a lot of detail. So these are just stability numbers as a function of zirconium content. And this green stuff up here, where you start getting zeros, that's a good sign. That means you're very stable. So what it told us is that as we add zirconium and approach this barium zirconate limit, fewer zirconium on one of the sublattices of perovskite, you get a lot of increased stability. So we saw a real clear advantage to adding zirconium. We just wanted to add enough to get stability, but not so much that we lost all our electrical conductivity. So that was kind of the sweet spot. So we tried a couple of different zirconium contents. 75 was a really aggressive amount. 0.2 was a much less aggressive amount. And we looked at some of the properties, like this surface exchange coefficient. And we looked at things like stability. And we found that if we went from about 0.2, here 0.25, all the way up to 75, and we looked at how the surface exchange coefficient survived over at least a few hundred hours, the greater amount of zirconium, the more stability we had, right? So we lost stability really fast when we had only 25% zirconium, lost it more slowly with 50, and maintained stability, maintained our high surface exchange coefficient quite well when we had 75% zirconium. So this is exactly as the computational screening suggested, that the zirconium would help stabilize our material. So that was very encouraging. So then we actually made the material and looked at the area-specific resistance of the material as a fuel cell electrode. Again, we want numbers that are down near 0.1 or below. And we made the direct material, and we made it with a couple of different electrolytes, but this is the kind of best electrolyte, are getting below 0.1, so that was encouraging. But this is up at about 1,000 Kelvin, which is about 700 or 800 or so Celsius. And when we cool down to 600 or so Celsius, where we might want to get to, we were back up here with an area-specific resistance of about 1. That's too high to use. So the material seemed encouraging, but wasn't really performing the way we had hoped. However, we realized that a lot of the problem, we did some analysis experimentally with our collaborators at the National Energy Technology Laboratory. We realized we didn't have very good electrical conductivity. So this wasn't a problem with oxygen transport. It was a problem with electrons at transport. So we realized if we mixed it with something that had good electrical conductivity, we could maybe fix the problem. So we took lanthanum, strontium, cobalt, iron oxide, which is a present day, the best commercial solid oxide fuel cell. And we mixed in our material with our 75% zirconium for good stability and good performance with this lanthanum, strontium, cobalt, iron oxide. And we used the electrical conductivity of the lanthanum, strontium, cobalt, iron oxide to kind of fix our electrical conductivity issues, but we kept our ability to do really good oxygen kinetics. And we made a composite of the two, hopefully getting the best of both worlds. And that actually worked quite well. If you're up near 800 Celsius, this is now a log scale. So we are at almost, well, if you're up near 900, we are at 0.01 in terms of area-specific resistance. If we want to target 0.1, lanthanum, strontium, iron, cobalt kind of maxes out about 750, 800 degrees Celsius. Now we can go down to all the way to 700 degrees Celsius. So we can gain 50 to 100 degrees in temperature lowering and still get adequate performance, maybe even a little bit below 100 degrees. And this was essentially the second or third time we ever made this material and made this composite. So with a little optimization, I think it's quite reasonable to imagine we could get down to 600 degrees Celsius. We just haven't gone through that process yet. So this was an encouraging result. And one thing I want to stress about this is we ended up at this material with a few tries after the whole computational screening process. So the efficiency of converging on it was extremely high. And it gives us a promising new material, at least when used as a composite, for achieving improved performance. Okay, so let me wrap up that story. We use these data-centric methods. We found, very surprisingly to us, and I think many other people, that you could add a lot of zirconium and still keep really good oxygen exchange. The electronic conductivity did suffer, but if we mixed it as a composite, we could get a very promising new solid oxide fuel cell cathode. And this material really emerged now as a promising composite type candidate for these types of technologies. And we were able to get there very quickly by using these computational screening methods. So that's kind of the main story I want to tell. There are a number of other stories. I summarized that story in a one-slide version. Let me just very quickly tell you a one-slide version of a different story, just to show you that you can run this type of approach over and over again with slightly different perspectives. So for example, after we found this material, we realized, a lot of the best materials actually move oxygen not by a vacancy mechanism, which is what our material uses, and almost all the commercial materials, well, all the commercial materials basically use. But oxygen can also be transported by what's called an interstitial mechanism, where it moves between lattice sites. Those materials are much less common. We know much less about how to design them, but they're very, very fast. These are the energies of migration of vacancy-mediated materials and interstitial materials from the literature. You can see the interstitial materials have very low migration barriers, even down to 0.2 or so electron volts, which gives you mobility at room temperature. Could be very exciting material if you could really design something like that that had a lot of oxygen available as an interstitial. So we thought, could we discover interstitial diffusers? So we went through the exact same type of, not exactly the same, but a similar type of screening process. Started with about 35,000 oxides, screened out ones that we thought, or focused in on ones that we thought had enough space to form oxygen interstitials, focused in on ones we thought we could synthesize, did calculations of the energetics of creating oxygen interstitials, of moving oxygen interstitials around, and got a small, short list of promising candidate materials. We picked one as one we thought we could make. There was a previous paper on how to make it, so we thought, oh, that won't be too hard to synthesize. Had very good predicted performance. It was lanthanum-4, manganese-5, silicon-4, oxygen-22. What is really interesting to me about this material, here's its crystal structure, is I would never guess that this material was of any interest at all. I'd never heard of this material. I knew nothing about it. No one had studied it when we began this project, at least. Other people have now. But it was kind of out of nowhere. And we said, it was really one of those crazy suggestions from the computer. But we took it at face value and said, fine, we're going to make it. And we synthesized it. We measured its oxygen conductivity. It is within a factor of 3 or 4 or 5 of the best oxygen conductors in the world. So it's a very good oxygen conductor. We measured its surface exchange coefficient. It is competitive with the top materials in the world. There's only one that we know of that was measured that had better performance, and it's kind of an outlier. So it's within the top few best performing surface exchanges. So it has extremely good oxygen kinetics, just like we had hoped, because it has this really fast interstitial transport. It does turn out to be an interstitial oxygen conductor. We just published that result a few months ago. So what's really nice about this example to me is not only were we able to find an interesting material, and we haven't really figured out yet how it will behave in different actual devices, because we haven't gotten to testing it yet, but it has really good basic materials properties for moving oxygen. We discovered it in one shot. It was the only material we tried, and it had really outstanding properties. And we never would have thought of it just on our own. The computer suggested to us, and in one try, we had something that was really exciting to work with. So that to us is really the dream of this kind of design. The computer does all this hard work. It comes up to you and says, maybe you should try this. You go, okay, I'll try it. and it really pans out to be something exciting and potentially transformative for the technology you're interested in.
There's a question. What does the D symbolize in the compound formula? I think the O22 plus D.
Sorry, yeah. So when you write the stoichiometry, this is the stoichiometric material, oxygen 22, plus D means extra oxygen that comes out as interstitial oxygen. If you write minus D, you mean you've lost oxygen, and those are vacancies. So this is a plus D material, and D represents the amount of extra oxygen in the material. I have one other example slide here that I don't have time to go through of another design scheme, very similar, another interesting material that came out of it, again, with only one type of, only one set of experiments was really needed. I won't go through the details in the interest of time, but what I want to stress is one can keep doing this with slightly different design goals and get different kinds of interesting materials. I do want to wrap up just for a couple of minutes about talking about machine learning as an alternative, well, really an extra part of this type of workflow. So let me skip this for the moment. That's some other related work that other people have done some really similar work to us, which is really excellent as well. I'll talk about ours just because I understand it better. But this is just an example of what one can do in terms of predicting area-specific resistance with a machine learning algorithm. So what we did here is we collected about 300 unique measurements, unique different compounds of measured area-specific resistance in a solid oxide fuel cell type environment. And we said, what elements are in those compounds? And we said, can I learn a pattern between the elements in the compounds and the performance? And that learning of that pattern is what we mean by machine learning. We used a technique called random forest, if people are familiar with different machine learning techniques. And this was our ability to do that. These are the predicted area-specific resistances on these compounds when they're left out of the fit. And this is the actual measured value. If they were perfect, the model would fall right along this dotted line. We clearly don't. The model is not perfect. On the other hand, there's clearly correlation here. We can tell materials with really low area-specific resistance from materials with really high area-specific resistance. And that is powerful because I can take a new compound and predict in 1/100th of a second an approximate value of its area-specific resistance. So now I can screen at a scale that dwarfs what we could do before with more complicated calculation. I could screen millions of compounds this way. An interesting way to test this is we took all the data we had and we trained our model only up to a certain year, and then we tried to discover the materials that came after that. And we asked, how well do we do? And a good way to measure that is just your precision and recall. This is the fraction of time you're right and the fraction of the materials you find. Let's just focus on recall. That's the fraction of materials that had yet to be discovered that we found using the machine learning model if we only trained on data up to a certain year. And the interesting thing is if you train on data up to, say, 2007, and you try to discover the materials that people found after that, we find about 80% of them. So certainly not all of them, but a very good fraction. And in general, it gets up to almost 90%. This is a sort of fluke of having very little data. But in general, what you find is with this type of machine learning model, by looking historically, we can, in fact, find most materials that people found by other methods using this type of machine learning model. So we haven't yet gone into the future yet, because the future hasn't happened. But what we hope is that now using this type of screening, we'll find a bunch of compounds that we won't have to find a much more laborious one experiment at a time way, but can find with these types of machine learning methods. And we think that's a very powerful approach to this type of materials discovery. It's still very new, so we're still learning how well that can work, but I think it's very promising. Okay, let me actually wrap up there. There's a little bit on some new techniques to collect data, but I think I'll skip those and just give a summary here. So what I want to send as a message here is that materials discovery in general has reached a sort of new level of efficacy, of speed, of ability to find new exciting materials. We've been doing this in fast oxygen conductors and surface exchange materials, active oxygen materials, and it really has arrived. You really can do this. In single effort, we can find a new interstitial conductor that seems promising. that kind of thing is now possible, and I think it's going to lead to an explosion of exciting new materials. I think machine learning is going to increase that even more as we gain more data, can find patterns in that data, and then use those patterns to make predictions another 10 or 100 or 1,000 times as fast as we can make them using more complicated molecular modeling methods. So we'll hopefully 10x things another level by using machine learning. And that will allow us to predict a lot of materials fast. I think that's going to keep coming. You do still have to make them and test them. That is becoming increasingly the challenge. We predicted this target material with maybe 6 months of work for our interstitial conductor. We then spent a year trying to get the data. And we had a handful of others, which we never really had time to look at. So more and more, I think the focus is going to have to be on finding ways to synthesize quickly, test quickly, maybe in automated ways, maybe in high throughput ways, so that we can explore all the exciting ideas that computers are suggesting for us. So with that, I will wrap up. Thank you. Happy to take any more questions. Thank you.
I guess I'll start off. What would you say is the biggest change in the last 5 years that's really enabled, these advances? That, what can you do now that you couldn't do 5 years ago?
Yeah. Let me throw out a few, but I'll go back 15 years. I'd say, well, it's good to go back 30 because that's when I was a graduate student. So that's a nice period I can talk about. When I began as a graduate student, we'd write papers where we do 10 calculations, maybe 15, with quantum mechanical simulations or molecular simulations, because they were hard and they broke a lot and it needed a lot of babysitting to get an answer. So what happened maybe 30 to 15 years ago is the ability to calculate basic properties of materials at a quantum mechanical level became robust and fast. And so a paper went from 10 calculations to 1,000 or 10,000 calculations sometimes. We're writing a paper right now. It's going to have 80,000 quantum mechanical calculations in. It took 6 to 12 months to put it together. So that was a big thing. That's speed of computers and stability of the codes. So that changed how many calculations you could do to get some data to work with. Then about 10 years ago, people started really putting online large databases of computed data because they could do the computation so robustly. So that scaled us up to databases that now have 100,000, 200,000, 1 million, 10 million calculated values in them that you can just download and use to look for patterns and correlations. And then I'd say in the last 5 to 10 years, we've begun to see machine learning algorithms. Their impact is still just emerging, I would say. But that's probably the third pillar, I think, that's gonna change what we can do. Thought about that. Yeah, there's something. Yeah.
Sure. Bring this over here.
Thanks. Yeah, I was curious, how difficult is it to physically synthesize in the lab these various compounds that you come up with by computer to actually fabricate them?
Yeah, that answer varies wildly. In our case, they're not very difficult because we pick them that way. So when we picked our interstitial material, we had a handful of interstitial materials that had been predicted. And we went and looked them up. And the one that had a nice, clear, clean paper that had successfully made it, that's the one we started with. So we knew a recipe to synthesize it. Even so, it took us weeks, I would say, to kind of get decent phase pure material. So it's not a huge effort. It's not super complicated, but you need to reserve a few weeks to kind of get it working and going. Now, we don't do a ton of experiments. Better labs may be able to do that more successfully. So it can vary a lot. If you get unlucky and you pick a new material, you could spend months trying to synthesize a pure sample of it. If you get lucky, it might take you 2 days. But the unknown is not a pleasant thing to face. So we went for something pretty conservative where other people had gone through that and figured out how to do it.
Also, I had another question. You mentioned a platinum. Were you being facetious, or does that have any potential applications in fuel cells?
So many fuel cells in the past used to use platinum electrode. not big chunks of platinum, but little nanoparticles and things of platinum on surfaces. Lower temperature proton exchange membrane fuel cells still use platinum as a core material. So it's not facetious to use it. One of the reasons these perovskite oxides are nice is that they are very effective and high performing and do not use precious metals. So we probably wouldn't add platinum into these. It's not inconceivable. You could make something useful that way, but it's not where you want to go. You want to go to cheaper, more earth abundant materials rather than less.
Question online. So this method appears to be a significant breakthrough. Is it being recognized in other fields of research yet?
So I would say the idea of doing this sort of computational materials design is well recognized. It has, if you look at sort of the number of papers that make use of it, they have grown increasingly. Increasingly, companies have people who do this kind of design. Every material science department, essentially, that does serious research in the country has somebody who does this kind of design. So if you look at funding agencies, they often expect a sort of computational component to what you're doing. So I'd say it is recognized in that way. Maybe one way to describe how it's recognized is that in 2011, there was an initiative to engage much more computation in material science called the Materials Genome Initiative. There's actually a nice picture of Obama announcing it when he was president. And it's been very effective at trying to drive many more resources into this area and grow the amount of work in this area. So people recognize that it was really important to help build it up. That was in 2011, and then that build out has happened over the last 12 or 13 years. And so now we have a lot of really valuable resources in this space. So.
I don't see any more questions online. Do you have any other questions? All right. Well, thank you so much for your presentation today. It's really insightful.
Thank you, and thank everyone online. Thank you.
We'll see you back in a couple of weeks.